Hi everybody, we are in section 6.3, so using the fundamental theorem to find definite integrals. So we're going to start off by looking at the fundamental theorem of calculus. So this is the FTC. This says if f is continuous on the interval a to b and big F is an antiderivative of little f, then we have the following computation. So the integral from a to b of little f of x dx equals big F of b minus big F of a. Okay, so this is what the fundamental theorem of calculus tells us. So if we want to compute an integral, all we need to do is take the antiderivative, right? So get big F, and then evaluate it at the bounds. So we take f, plug in b, and then subtract, and then take f and plug in a. Right? So this gives us a nice, quick method of finding the values of definite integrals, okay, which just gives us area under the curve. So now we can find area under a curve exactly without approximating and find it much more quickly as well. Okay, so let's look at this first one here, this first example. So compute the integral from 1 to 3 of 2x dx. So to start off, we do need to know the antiderivative. So the antiderivative of little f equals 2x is, that's big F of x. Antiderivative of 2x is x squared. So to compute the integral, so we get integral from 1 to 3 of 2x dx. That's going to be antiderivative at 3 minus antiderivative at 1. Okay, and so antiderivative, again, is x squared. That's over here. So that's going to be 3 squared minus 1 squared. Okay, which is, of course, 9 minus 1, which is 8. Okay, so this gives us the area under the curve for the graph 2x from 1 to 3. Okay, and that's something we could compute geometrically to verify. Notationally, I want to put this in here. So notationally, we're going to write it in the following way. So we have integral from 1 to 3 of 2x dx. We write that equals the antiderivative, so x squared, and then we draw this vertical line with 1 and 3 on it. And this is what we call the evaluation bar. Okay, so this is the evaluation bar. And it just signifies that we have already taken an antiderivative. Okay, so the integral portion is done, but we still need to evaluate. We still need to plug in the 3 and the 1. Right, so this would tell us then we get 3 squared minus 1 squared, which is the 8. Okay, so it still gives us the same thing as we had before. Okay, but this is the more common notation that we're going to see here when we take that antiderivative. Now, if you're wondering, when we were computing antiderivatives, we had that arbitrary constant, the plus c. Do you need to include the plus c for a definite integral like this? No, you don't. You don't have to include it because it's unnecessary. When you're actually plugging in specific bounds, there is no arbitrary nature to that. It's very fixed. It's very finite. Okay, it's one specific value rather than a family of functions. So you don't need to include the plus c. However, if you wanted to include the plus c, you could. So let me just put this right here. So could we include the arbitrary constant? The short answer is yes. You could include it if you wanted to, because it doesn't have any effect. So if we instead we used the antiderivative to be x squared plus c, then we would get the integral from 1 to 3 of 2x dx. Right, that's x squared plus c from 1 to 3. That would be, oops, that would be 3 squared plus c minus 1 squared plus c. So that would give us 9 plus c minus 1 minus c. And you see we get that cancellation there, and that gives us the 8. And that would happen every time. Okay, so that's not just an anomaly. So if you do include the plus c is just going to disappear in your calculation regardless. So when it comes to a definite integral, I would just leave it out. Just don't even include it. You don't need it for a definite integral. Okay, indefinite integral with no bounds, you do have to include it. Okay, so let's look at some more examples here. So compute the following definite integrals. So we have integrals 0 to 2 of 6t squared dt. So we need to compute the antiderivative of 6t squared. So the square should become a cube, right? And notice I have a factor of 3 in the 6 that I can pull from. So this is going to become 2t cubed. Okay, right? And if you're not sure about that, just take the derivative of this, and it gets you back to 6t squared again. Okay, and then this gets evaluated from 0 to 2. So that's going to be 2 times 2 cubed minus 2 times 0 cubed. And that's just going to be 16. Okay, remember the definite integral gives us a number, right? It gives us a specific value because we're talking about area here. So next up, we have integral from 1 to 2 of 8x plus 5 dx. So let's take some antiderivatives. Antiderivative of 8x, so that's x to the first. It's going to become x squared. So this is going to become 4x squared. And then antiderivative of 5 is 5x. And this gets evaluated from 1 to 2. Okay. Now when doing evaluations like this, it is important to make sure you keep all of your terms straight. And I would say be very careful with your parentheses, because that can really help you not mess up the negatives in particular. So this is going to be 4 times 2 squared. Oops, let me rewrite those 2's. 4 times 2 squared plus 5 times 2 minus 4 times 1 squared plus 5 times 1. Okay. The reason that these parentheses can be so important is because this negative here applies to both of those, not just one of them. And if you don't put the parentheses, sometimes you can apply it like to the 4 but not to the 5, and then that ends up giving you a wrong answer. So let's see what we get here. So 4 times 4 is 16, plus 10 is 26. And then minus 4 plus 5 is 9. So we get 17. Alright, and then last one down here. So integral from 0 to 1 of 8e to the 2t. Okay. So the antiderivative of e to the 2t is, again, e to the 2t divided by 2, right, to balance out, because that has a 2t up in here. So this is going to be 8 over 2, which is 4. E to the 2t, evaluated from 0 to 1. Okay. So this gives us 4e squared minus 4e to the 0. E to the 0 is just 1. So this is 4e squared minus 4. Alright. And that's the exact answer, and that's the one we want. We don't want those approximations, just leave it exact, and that would be perfect. Okay, let's look at this next one. So write a definite integral to represent the area under the graph of f of t equals e to the 0.5t between t equals 0 and t equals 4. Then calculate the area. So to compute area, we're setting up this integral. So t is going from 0 to 4. And our integrand, that function on the inside, is e to the 0.5t dt, indicates that the variable is t. Okay, so that's the setup of our integral. And now, let's go ahead and take an antiderivative. So the antiderivative of e to the 0.5t is just going to be e to the 0.5t again. Now I'm going to do a couple of intermediate steps just to show you here, but then I'm just going to write the final version. This would be over 0.5, right, to balance out that power there. But this is the same thing as dividing by 1/2, which is the same thing as multiplying by 2 over 1. Okay, so instead of dividing this by the 0.5, I'm just going to multiply it by 2. And that will have the same effect and saves me a little space. And this gets evaluated from 0 to 4. So we get 2e to the, so 0.5 times 4 is 2, minus 2e to the 0. Again, 2e to the 0, that e to the 0 is 1. So this is just 2e squared minus 2. Okay, and that is the value that we get. And as always, leave it exact. We don't want to try to approximate this. I'm having trouble writing my 2's here. There we go. Okay. So let's take a look at the next page here. So improper integrals. So an improper integral is a definite integral where one or both of the bounds are infinite or the integrand is unbounded. So interpret and estimate the value of the integral from 1 to infinity of 1 over x squared dx. Now, of course, infinity is not a number, so how can that be an upper bound? Well, it's technically not a bound because this literally means it's unbounded, right? If it's going all the way to infinity, it just means that we're letting the area grow forever. And the question is that we need to ask is the area growing so large that it's just going to get infinitely big, right? Could this area just be infinite? Or is the area under the curve so small as we get out to, towards infinity, that it ends up not really adding anything meaningful to the integral? Okay, so let's first talk about kind of what this means. So interpret and estimate this value. So interpret, so this integral gives the area under the curve, under the curve, or I should say under the, it doesn't matter, under the graph of 1 over x squared from t equals 1 to infinity. The way that we're going to proceed in solving improper integrals like this is we're going to estimate. So let's estimate with some finite integrals. Okay, so we don't really have the tools, at least in this course at this time, to properly evaluate this improper integral, but we can get a pretty good idea of what's happening using some finite integrals that we are able to calculate. Okay, so what's really going on here is we have the graph from, there we go, the graph of 1 over x squared looks something like that. Okay, because it's asymptotic, it has a vertical asymptote here at the y-axis. And we're starting right about here. And that's x equals 1. Okay, and then x is just going to head off in that direction. Obviously that's the y. And we are looking for this area right here. Okay, heading off towards positive infinity. And like I said, the question is, so here's the curve, this is 1 over x squared. This area in here is the integral from 1 to infinity of 1 over x squared dx. Okay. But the question is, right, does this area just keep adding and adding and adding and adding forever and just keep growing infinitely large? Or are the values, as we start getting out to kind of the outskirts here, this function is going to get so close to the x-axis that these areas are going to get so small that they really don't contribute anything to the overall area anymore. So that's the question, is does this result grow infinitely large, or does it actually kind of stop at a specific value? So let's look at a couple of finite integrals to try this out. So let's start off with integral from 1 to 10. Okay, integral from 1 to 10. Just nice easy numbers here. Okay, take the antiderivative of 1 over x squared. So that's going to be negative 1 over x. And you'll need the power rule for that because it's x to the negative 2, right? That's how we can rewrite that using the power rule. Evaluated from 1 to 10. So that's negative 1 over 10 minus negative 1 over 1. So that's negative 1/10 plus 1. So 9/10, which as a decimal is just 0.9. Okay. So that by itself doesn't really give us much, so let's do another one. Let's step up the scale a little bit. So integral from 1 to 100 of 1 over x squared dx. So antiderivative, negative 1 over x, evaluated 1 to 100. So that's negative 1 over 100 plus 1, right, just like we had over here. So that's going to give us 99 over 100, which is 0.99. Okay, and let's do one more. Integral 1 to 1,000 of 1 over x squared dx. So antiderivative, negative 1 over x, evaluated 1 to 1,000. So that's negative 1 over 1,000 plus 1. So that's 999 over 1,000, which is 0.999. So you might be able to see what's happening here. Notice that as this upper bound starts getting higher and higher and higher, right? And we can just keep doing this. Notice that these values are never actually going to cross the threshold of 1, right? It's always going to be, 1 minus some small number, 1 minus a smaller number, 1 minus an even smaller number. Okay, and this is the pattern that is repeating over and over again here. So this integral, this area, will never cross 1. And as x goes towards infinity, the value of this integral is actually approaching 1. So what we can say is we have a special term for this. When the area actually approaches a specific value, it doesn't get infinitely large, we can say the value converges to 1. Okay. We say the value converges to 1. So that means that all the values as we go towards infinity, the area is just approaching 1. It's not growing infinitely large. Okay? So, in conclusion, we can say the integral from 1 to infinity of 1 over x squared dx